Hi, and welcome to video 2 on U-Substitution for Calc 1. This is again video 2 of what is a 3-part series for U-Sub in Calc 1. So this is more U-Sub, and then the third video we're going to take a look at some rational functions and integrating those, and we're going to look at why is each one a fraction, because they each have a different reason for being a rational function. So this is more U-substitution, and let's see. Most of these are going to be indefinite integrals. However, the very next one we will look at will be definite, so you can look at how to change the bounds and make sure you're in the correct variable. So if you have started U-substitution, it should be fairly clear to you by now, hopefully, that the U is what is inside of another function. So it's where your composite function lies, or in other words, this 2x minus 1 is inside of a 1/2 power or inside of a square root. So the inner piece is our U. And then we said let's solve for du. And so the derivative of 2x is 2 dx because the derivative of minus 1 is 0. And what we did was solve for dx, and I want to prepare those of you going on to Calc 2 for what's considered to be an inside-outside component here. So what happens is we already have this dx here. Here's my dx, right? But I don't need it to be 1 dx. I need 2 dx in order to substitute that for du. So what we're going to do is we're going to make this say 2 dx. So we're going to multiply this in essence by 2. I'm not going to rewrite the dx just for confusion. But really I'm going to multiply this by 2 so that that's 2 dx. And then this 2 dx part is going to become du. Well, I can't just multiply an equation by 2 because I want to. So what I have to do is somewhere else divide my antiderivative by 2. Or I could multiply it by 1/2. So this is considered the inside-outside technique. And this was actually the only way that I learned U-substitution. I never even learned it solving for dx, but either way will work. So the inside, you needed to put a 2 to make that match what you needed for your du. So then on the outside, I had to put its reciprocal, because again, 1/2 of 2 is 1. I'm really just multiplying my antiderivative by 1. I'm not changing its value. I'm just changing the way it appears. It's the same thing as saying 3 over 6 is equivalent to 1/2. I'm not changing its value. I'm changing the way it appears. Whether I go from the left to the right or from the right to the left, I can either think of it as multiplying by 3 over 3 or dividing by 3 over 3, but those are equivalent fractions. I'm doing the same thing here with my integral. I'm multiplying by 2 on the inside and multiplying by 1/2 on the outside. So I have the du part, okay? So all this is going to turn into du. I have the square root of u, so let me just go ahead and rewrite what my antiderivative is going to look like now. So it's 1/2. I still have that x there, and that is square root of u, and then remember that 2 dx was du. And if you're very uncomfortable with that, I know, just hang on for a few examples. I think it'll get better as we go. The problem with this one is that we have that extra variable. And if you remember in the last video, I did tell you we would address the extra variable case, and here it is now. You wrote a relationship between u and x that we decided in place of the 2x minus 1, we would put a u. That's how I got the square root of u in this antiderivative. That relationship actually relates x and u in any form that you want. So for example, I can solve that for x. What that's going to do is tell me what is x in terms of u. So I can add 1 to both sides and then divide by 2. And now I know x is now in terms of u, so I can make that substitution as well. So it's a double substitution problem. So I carry my half. My x is really u plus 1 over 2 times the square root of u du. I am going to move that extra half out front, so that becomes 1/4 times the antiderivative u plus 1 times the square root of u. And now I need to be able to integrate that. Well, again, we don't have a product rule, quotient rule, etc. for anti-differentiation, so I do need to multiply this out. And if I think of u under the square root as being u to the half, I can then distribute that into those parentheses. So this will become 1/4. Then it is u to the, I would same base, add my exponents, so a half and 1 would be 3/2 plus 1 u to the 1/2, and I'm integrating still with respect to u. So I can integrate this, keeping your 1/4 out in front of everything. I'm going to leave a space because, again, I'm integrating with a fractional exponent. So I'm going to leave a space, and this is going to be u to the, add 1 to your exponent, would be 5/2. And I'm not going to divide by 5/2. I'm going to multiply by 2/5. Plus, I'm going to leave a space because, again, I have a fractional exponent, so I know I'm going to put a coefficient in front of there. This will be u to the 3/2 times 2/3, and all of that plus c. And whether you put your plus c in that 1/4 or not is up to you. But I do need to put my u's back in. If you want to distribute your 1/4, you can. So this will be 1/10 times my u to the 5/2 plus, and this, if I distribute that 1/4, would be 1/6, whatever my u is, to the 3/2. And I'm just going to go back up here in 1 second and look and see what my u was. My u, all the way back at the start, was 2x minus 1. So I'll put that in now. 2x minus 1, 2x minus 1. Okay, let me show you another one with the inside-outside before we do another variable in a definite integral. So if I allow my denominator, like we would normally, to be my u, I would let this 5x cubed minus 1 be my u. So my du here in green is 15x squared dx. So immediately I recognize that's not what I have. I have in my numerator 2x squared dx. So what we're going to do is rewrite this, move that 2 out front, just like I did in red, move it out front, and then you can multiply, because you need 15x squared dx, and right now you only have x squared dx. So I can multiply the inside by 15 as long as I divide the outside by 15 or multiply by 1/15. And then what I'll notice is I just have 2/15 on the outside of my antiderivative. The numerator is du, the denominator is u. That integration is the natural log. Just don't forget your absolute value bars to make that domain match. Okay, so let's go back up and do a definite integral one so we can see bounds, okay? So what happens here, and I'm going to show you the inside-outside again, I just want to focus on the bounds on this one. So when you're looking at the original problem, you're integrating x squared, I put that 3 in, times the quantity x cubed plus 8 squared dx. Okay, so with respect to x. Well, no matter what technique you're using for integrating, it's really important to note that you're integrating with respect to x. So my functions are all in terms of x, but that also means these are bounds x equals 4 and x equals -2. And sometimes people will literally put x equals 4 at the top of their bound so they know without a doubt that it is x equals 4 even if you're going towards u's. So the inside piece here was this x cubed minus 8, so I let that be my u. And then if that's the case, du is that 3x squared dx, which I highlighted in tan. I only had 1x squared dx. So I multiplied the inside of my integrand by 3 and multiplied the outside by 1/3. Again, 1/3 of 3 is 1. I'm not changing the value of anything. I'm only changing the way it temporarily appears. Then that 3x squared dx will get replaced with du, and this inside piece will just be u squared. So I'm only integrating u squared du, which is a not bad integration. But here's what I wanted to draw your attention on. I have dots right here right now because you have a choice to make. I cannot put -2 to 4 on my bounds because these are x's. So some people will say x equals, but then you're going to have to, no matter what, not stop here at u, right, even after you integrate, because your bounds are x's. So you're going to have to go back all the way to x equals, what was u? U was x cubed plus 8. So you're going to have to go back and put the function when you're done back in terms of x. Or you cannot put your bounds on right here in terms of x, but rather I can figure out what my bounds are in terms of u. So let's change the bounds, okay? Let's change the bounds so they are also u equals. So I wrote the relationship, right? U equals x cubed plus 8. And the original bounds were x equals -2 to x equals 4. So if x equals -2, put that in for x. -2 cubed plus 8 is 0. So my lower bound is x equals 0. And that's my lower bound because this was the lower bound. My -2 was the lower bound if I was in x's, so 0 will be the lower bound in terms of u's. So on all these u's, I could have put a 0 for my lower bound. And then for the upper bound, you're going to take the same relationship function that you wrote, u equals x cubed plus 8, and you're going to put x equals 4 in. So 4 cubed is 64, plus 8 is 72. And this will be my upper bound, again in terms of u. So I could go back to all these upper bounds and say that my upper bound in terms of u is 72. What I have to make sure of is that if I have a definite integral and I have an integral in terms of x like I do in the beginning antiderivative, my bounds then are x's. But as soon as I change and I now have an integral all in terms of u, my bounds have to also be u's. Okay? So I can change my bounds accordingly. So that would be going from 0 to 72. I integrated and got u cubed over 9, or 1/9 u cubed. So that would be 1/9 of 72 cubed minus 1/9 of 0, which is 0. So it's 72 cubed over 9. So just make sure that your bounds will match. And certainly this is something that you can check on your calculator, because remember, all of these definite integrals we can check. So I can pull up my calculator here. Okay, and now that I have my calculator, I am in the math print mode, or the new software. So if I hit math 9 or function integrate, I'm going to type in exactly my problem from the beginning. So I was integrating from -2 to 4 initially, and I had x squared times the quantity x cubed plus 8, that quantity squared. I want to make sure this is going well as I'm typing here, and dx. All right, hit enter. 41,472. That's exactly what we thought. You can also go to your U's and see if you changed your bounds accordingly. So I can say math 9. I got to the point where I thought this was equivalent to the antiderivative from 0 to 72 of, and I can change the variable to just be x squared dx, because it doesn't matter as long as you're single variable. It doesn't matter what you're typing in here. You know on your paper this was your U's and these are your U's, so as long as they all match on your paper, it's fine. I'm going to take that answer though, and I'm going to have to divide by 3, or you can insert a 1/3 in front of it. So you can say second delete or insert here a 1/3, and I'm going to do well, see, and I don't prefer that. I like just dividing my answer by 3. So I'm going to go here, calculate it, and just say divided by 3. 41,472. So if I think for a second I didn't change my bounds right, I could certainly check that by checking both antiderivatives. After you anti-differentiate, that's just your computation, but it should work either way. Okay? That's all about changing your bounds. So let's get back to a couple other examples that are indefinite integrals so we can practice more U-substitution. Okay, so let's do U-substitution on this number 3 here that I just wrote down. It is sine of x over cosine squared x dx. So the part that is the function inside of another function would be that cosine of x, because it is being squared, of course, in the denominator. But again, I can write u to the -2 if I need to. So let's let u be the cosine of x. So then du, my derivative of cosine x, would be negative sine x dx. And let's see what we have and see if we have that du in our original problem. And I do. I have sine x dx, so I just need to multiply the inside by a -1, so I will multiply the outside by a -1. So then this whole negative sine x dx part is going to be replaced with du, and the denominator gets replaced with u squared. Again, it doesn't care. U-substitution, it doesn't matter what the u actually was, whether it was trigonometry functions or trigonometric functions or e functions or natural log. It doesn't matter as long as the u and du parts match up. So then if I go through one quick rewrite here, I should be able to integrate this. Right? So I'm going to keep the negative out front just for a second here. This is going to be u to the -1 over -1. Don't forget your plus c. And so then this will be +1 over u, if I just write that in terms of variables without, negative exponents. And u was cosine x. Certainly is a fine answer to have. We also do have a definition for the reciprocal of cosine x, which is secant x. Either one, neither one is considered more correct. Just depends on what they ask for. So I could go through that problem and do U-substitution. Now, trigonometric functions are often really friendly. So take a look at this. Sometimes people see, you know what, I don't want to start with U-substitution. I just want to try a rewrite first. I'm going to separate those cosines out because sine divided by one of those cosines is tangent x, and then 1 over cosine is secant x. right? And so cosine times cosine in the denominator is cosine squared. So all I did was rewrite the original there, and I'm actually anti-differentiating tangent x secant x. That was why we went through a lot of those trig identities to see, well, gosh, is this equivalent to this right here? Because if it is, I would much prefer to have the antiderivative of secant tangent because I know that function is secant. Because secant x derivative was secant x tangent x dx. So either way, whatever you see is going to be more efficient for you. There's kind of not one one-size-fits-all model for that one. All right, so let's look at number 4 here and look at this extra variable case again, and also look at the inside-outside again. So again, I hope that identifying our u is not our source of confusion, but in this case, I want u to be 1 plus x squared. And then my du is going to be 2x dx. All right, so this is going to take a little bit of rewriting here. So I want to reserve one of the x's, but I have a lot of them outside of that square root of u part, right? Because this is all going to be taken up by square root of u. The rest of it, I would hope, would be taken up by my du, but it's not going to be. It's going to leave behind some extra things. So what I'm going to do is rewrite this one time as x times x to the 4th square root of 1 plus x squared dx. And let's see if you can understand why. I need one of these x's for my du. So here it is. So I'll kind of highlight my du stuff here. Right? But I'm going to need two of them, keep in mind. So I'll put the 2 in there and the 1/2 out in a second. But this was x to the 5th in front of my square root. I'm just separating it into those that I need and then those that are going to be extra. And then I recognize that I need 2x dx. So I'm going to multiply this by 2 and multiply outside by 1/2 because again, half of 2 is 1. So far, here's where I'm at in my substitution. I have a 1/2 out. This 2x dx is going to be du. Nothing has happened yet with that x to the 4th. And then this part right here was my u, so that's square root of u. I can't integrate this in single variable Calc 1 where I have two still variables. So that means I'm going to have to write the relationship that I wrote, or that substitution, that red substitution here that I wrote for u. I'm going to have to use that again and do substitution twice. Well, I don't need to go all the way down and solve for x. If I subtract 1 from both sides, I have that equation solved for x squared. And what we should recognize is because x to the 4th is x squared squared, I can square both sides, not individual terms, both sides. So this is really u squared minus 2u plus 1 if we wrote it all the way out, or expanded form. So this gets me to 1/2 times the antiderivative x to the 4th is really that u squared minus 2u plus 1. I still have that square root of u there that's been hanging on. And now I can multiply one more time, like I can distribute that square root of u, and then I'll be able to integrate. So I have 1/2 on the outside. And then if I distribute, I'm multiplying in u to the 1/2. So that'll be u to the 5/2, right? Because you add your exponents when you multiply with same base, minus 2u to the 3/2 plus u to the 1/2, and I'm integrating with respect to u. Okay. Again, pause, rewind, do whatever you need, right? If this went too fast at one point or too slow, you can always fast forward and see if you can pick up from where I'm at. So I'll integrate this. Now I'm going to make it a little bit easier on myself. I'm just going to put a parenthesis where the u's are so that I can just go back and put that u, which was 1 plus x squared, when I'm all the way done. So when I integrate u to the 5/2, I'm going to leave a space. I'm going to add 1 to my exponent. And again, instead of u, I'm just going to put parentheses here. So if I add 1, it'll be to the 7/2, and it'll be times 2/7. And my u was 1 plus x squared. If this is too much, you do not have to do it all in one step here. Minus 2, I'm going to leave a little bit of space, put a parenthesis for my base, add 1 to your exponent. That would be 5/2. So I'm going to multiply this by 2/5, and my u is 1 plus x squared. And then plus, leave a little bit of space, again, my base. Now it'll be add 1 to my exponent to the 3/2, and multiply by 2/3, and my u, or base, was 1 plus x squared, all plus c. You can leave it like this. You can distribute your half. Since I had to rewrite it anyway, me writing all these u's really didn't save me all that much writing. But this is going to be 1/7 times 1 plus x squared to the 7/2 minus, if I distribute the half, minus 2/5, 1 plus x squared to the 5/2. And again, don't forget you're distributing that half, so this becomes 1/3, 1 plus x squared to the 3/2, and plus c. Again, you don't have to distribute that half in. That's entirely up to you. Okay, one last question. I just want you to see the inside-outside one more time in completion to see if this makes sense to you, and to see if you can start doing this sort of on your own. If my denominator is the u, now it's not to a power. I'm just going to say u is 5x minus 1. du then is just that constant 5 times dx. Well, I don't have a 5 in my problem, so I multiplied inside by 5, outside by 1/5, because that is, again, a product of 1. I'm not changing the value. I'm only changing the way it appears. Instead of that 5 dx, I'm going to write du, so that's what went into that numerator. My denominator was u, but I did have that 1/5 out front. Don't forget about it. It's the most important part. And if I thought this was power rule, I might try it and say that I'm integrating u to the -1 du. But when I add 1 to that power, I get 0. And divide by 0, I know, oh yeah, it's not the power rule. That is the natural log. And just don't forget your absolute value bars, because that's what makes your domain match. So I hope you found part 2 of this video over some of the more complicated U-substitution problems. I hope you found it helpful. Thanks for watching. There is a part 3 to come.